What if I told you that time, something we all take for granted, isn't as straightforward as it seems? From the rising and setting of the sun to the unceasing tick-tock of a clock, time governs our lives. But what exactly is time? It's not just the seconds, minutes, and hours on a clock face. No, time is a fundamental dimension, as essential to the structure of the universe as space itself. The journey of understanding time began centuries ago, with early civilizations using the cycles of the sun and moon to mark their days and seasons. Through these natural clocks, humans first established the rhythms of daily life. But as our knowledge expanded, so did our curiosity about the nature of time. Enter the world of physics, where time plays a starring role in the grand theater of the cosmos. Here, Sir Isaac Newton once described time as an ever-rolling stream, flowing evenly and unaffected by the events within it. This view held sway until a certain patent clerk turned physicist named Albert Einstein turned the concept on its head. Einstein proposed that time, far from being an independent and steady current, is intricately linked with the fabric of space. His theory of relativity introduced a mind-bending idea: time is relative. It can stretch and compress, influenced by speed and gravity. Imagine a universe where your time could pass at a different rate than someone else's simply because you were moving faster or situated near a massive object like a black hole. This groundbreaking idea transformed our understanding of the universe. Time wasn't just a backdrop for events. It was an active, dynamic participant in the cosmos. And yet, despite our leaps in understanding, time retains its mystique. Modern physics continues to uncover layers suggesting time may not even be as linear as we perceive it to be. So, buckle up as we dive into the enigmatic nature of time. Every day we check our watches and clocks, but what are we really measuring? Time, in its essence, is the invisible thread that stitches the fabric of our everyday lives. It dictates when we wake up, work, eat, and sleep, orchestrating our daily routines with precision. Consider the clock, an omnipresent guardian of our schedules. From the moment the alarm buzzes in the morning to the last check before lights out, the clock is our silent yet insistent companion. This relentless tracking of time isn't a modern obsession. It traces back to ancient civilizations who aligned their activities with the sun's journey across the sky, using sundials to mark the hours. As societies evolved, so did timekeeping devices, from the flowing sands of hourglasses to the intricate gears of mechanical clocks, and finally to the precise oscillations of atomic clocks. These advancements reflect humanity's relentless pursuit to measure time with ever greater accuracy. Clearly, time rules our daily lives, but how does it behave beyond our earthly experience? Scene script: enter Einstein, who threw a curveball into our understanding of time. Albert Einstein, with his hair as wild as his ideas, introduced the world to the theory of relativity in the early 20th century. This wasn't just any theory. It was one that would change how we see the universe forever. At its core, relativity tells us that time is not as fixed as your morning alarm might suggest. Let's break it down with a simple analogy. Imagine you're on a train moving close to the speed of light. To an observer standing on the platform, your clock on the train seems to tick slower than theirs. This phenomenon is known as time dilation, a mind-bending reality where time literally slows down as you move faster. But speed is just part of the story. Gravity also plays a pivotal role. Picture a massive object like a planet or a star. This object bends the fabric of space around it, creating what we might visualize as a well. The closer you get to this gravitational well, the slower your time passes compared to someone far away from it. This is why time on Earth ticks slightly slower than time in space. This concept was spectacularly confirmed by placing precise clocks on airplanes. These clocks were flown around the world and then compared to clocks that stayed on the ground. The results were clear. The clocks on the planes, moving at high speeds, had ticked slower than their grounded counterparts. So, what does all this mean for us and our daily lives? On a practical level, not much, unless you're planning interstellar travel or aiming to orbit a black hole. But on a philosophical level, it's profound. We are living in a universe where time is malleable. This means that time is not a constant flow, but is flexible, influenced by speed and mass. Imagine for a moment the possibilities if we could harness this cosmic quirk. What strange and wonderful futures might await us in a world where time is truly in our hands? Now, imagine a place where time could theoretically stop. Welcome to the enigmatic world of black holes, where the usual rules of time and space undergo profound transformations. Black holes are regions in space where the gravitational pull is so intense that nothing, not even light, can escape from them. This extreme gravity has fascinating effects on time itself. At the heart of a black hole lies the event horizon, a boundary beyond which nothing can return. Approaching this boundary, an observer would experience some of the most extreme time dilation known in the universe. According to Einstein's theory of relativity, time, as influenced by gravity, is not a constant. The stronger the gravitational pull, the slower time passes. Imagine dropping a clock into a black hole. As it falls toward the event horizon, an observer far from the black hole would see the clock's ticks slowing down, more and more approaching a standstill. This is not just a theoretical scenario. It's a consequence of how gravity influences time. The clock's time, from the perspective of a distant observer, would literally appear to freeze as it nears the event horizon. Inside the event horizon, the concept of time becomes even more abstract. Here, space and time are so warped that time itself points inevitably towards the center of the black hole. This leads to some strange but theoretically possible scenarios where time behaves in ways that defy our normal understanding. The implications of such extreme time dilation are vast and varied. For instance, if one were able to orbit just outside the event horizon, theoretically, they might witness centuries pass by in the outside universe in what feels like just hours for them. This aspect of black holes challenges our understanding of temporal progression and continuity. Black holes, thus, serve as a natural laboratory for testing the limits of our understanding of both time and gravity. They are not just fascinating celestial objects, they are also nature's own time machines. At the smallest scales, time plays by even stranger rules. Dive deep into the quantum world, and the traditional ticking of the clock doesn't quite apply. Here, particles pop in and out of existence, and the very fabric of reality behaves in ways that can bend the mind. Quantum mechanics, the theory that describes the behavior of particles at the smallest scales, introduces a concept where time itself might be a result of more fundamental phenomena. One of the most intriguing ideas is that time might emerge from quantum entanglement, the mysterious connection between particles, no matter how far apart they are. When particles become entangled, the state of one instantly influences the state of another, a phenomenon that baffled even Einstein, who famously referred to it as spooky action at a distance. Experiments in quantum mechanics have shown scenarios where cause and effect seem to be reversible, or where actions seem to occur without a preceding cause, challenging our everyday understanding of time's arrow, always pointing forward. For instance, in the quantum world, a particle can exist in multiple states at once, through a property called superposition, until it is observed. This blurs the line between past, present, and future, suggesting that on the quantum level, these distinctions might not be inherently defined. The concept that time might not flow in the quantum realm opens up mind-bending possibilities. Consider the quantum experiment with a so-called delayed choice setup, where actions performed at the time of measurement can retroactively change something that happened in the past. This experiment suggests that if we scale down to the very fabric of the universe, the flow of time might be an emergent property that doesn't exist by itself. In the quantum realm, time might not even flow at all. This insight could lead us to reconsider how we perceive time, not as a universal constant, but as a complex, layered phenomenon that varies with our understanding of the universe. As we continue to explore these depths, the nature of time could unravel even more mysterious and fundamental truths about the universe. Despite all these complexities, why does time seem to move only in one direction? It's a question that has puzzled philosophers, scientists, and thinkers alike for centuries. Enter the concept of the thermodynamic arrow of time, a principle that might shed some light on this mystery. At its core, this concept revolves around the idea of entropy, which is a measure of disorder or randomness in a system. Imagine you have a neatly arranged stack of papers. If you were to bump into the table, the papers would likely scatter, moving from a state of order to disorder. This increase in entropy is natural and expected in our everyday experiences. In essence, entropy tends to increase over time in an isolated system like our universe. This idea is beautifully illustrated by the simple act of breaking an egg. When an egg is dropped and breaks, the shell shatters and the contents spill out, moving from a state of order, intact and contained, to a state of chaos, broken and spread out. This transformation is a one-way street. No matter how much we might wish it, once broken, the egg cannot spontaneously reassemble itself. Why is that? It's because there are vastly more ways for the parts of an egg to be scattered than there are for them to be neatly assembled into a whole, unbroken egg. This vast probability disparity makes the reverse process exceedingly unlikely, thereby demonstrating the arrow of time. This irreversible nature of events where entropy increases shows why time itself appears to us as moving relentlessly forward. We remember the past, but not the future. We age, and we witness the decay of once new objects. Each of these phenomena aligns with the arrow of time, pointing in the direction of increasing entropy. The irreversible nature of events defines our everyday experience of time. So as we go about our days, the flow of time we perceive, always marching forward, never backward, is intimately tied to the relentless, ever-increasing disorder around us. This understanding not only deepens our grasp of time, but also connects the dots between abstract scientific principles and the tangible progression of our daily lives. From science fiction to serious science, time travel captures our imagination. Imagine stepping through a wormhole and emerging at a different time and place. It sounds like pure fantasy, but some theories in physics suggest that wormholes could, in theory, allow for such a journey. These hypothetical shortcuts through space and time are not just exciting plot devices, but are based on solutions to Einstein's equations of general relativity. Now, let's weave in cosmic strings, another intriguing concept from theoretical physics. These are hypothesized one-dimensional defects in spacetime, left over from the early universe. If these cosmic strings exist, and if they ever were to form a loop, they might create conditions for time loops, allowing for travel to the past. However, the existence of cosmic strings remains unconfirmed, and the practicality of using them for time travel is still a topic of debate among physicists. But here's where it gets really interesting: the paradoxes. Consider the famous grandfather paradox. If you traveled back in time and inadvertently prevented your grandfather from meeting your grandmother, you would never have been born to travel back in time in the first place. This paradox presents a logical inconsistency, challenging our understanding of cause and effect. Or think about the lesser-known bootstrap paradox, where an object or piece of information sent back in time becomes trapped in an infinite cause and effect loop. For example, imagine you received a scientific formula from a future self, only to later send it back to your younger self from the future, with no original discovery ever taking place. These mind-bending scenarios highlight significant issues with the concept of time travel to the past and suggest potential limits on the ways the universe allows causality to function. Time travel remains a tantalizing concept that straddles the line between fantasy and potential future reality. What does the future hold for our understanding of time? As we venture further into the unknown, the riddle of time continues to captivate and confound the brightest minds. Imagine a world where time isn't just something you watch pass on a clock, but a dimension we can understand, predict, and perhaps even manipulate. The journey into this future is as thrilling as it is uncertain. In the realm of quantum mechanics, scientists are already peeking behind the curtain of time's enigmatic nature. Quantum computing, a technology still in its infancy, holds promise for modeling time in ways we've barely begun to conceive. These computers, harnessing the peculiar behavior of quantum bits, might one day crack time-related puzzles that classical computers can't touch. Could they perhaps simulate entire universes, allowing us to observe how time behaves under different laws of physics? Then, consider the advances in gravitational wave astronomy. Just as ripples in water spread outward when a stone is tossed in, massive objects like black holes and neutron stars create waves in space-time when they collide. Detecting these waves has already helped confirm aspects of general relativity and may soon offer deeper insights into how gravity influences time. Moreover, there's the tantalizing possibility of time crystals. These new phases of matter oscillate in time without consuming energy, potentially teaching us new ways to think about and utilize the temporal dimension in technology and materials science. As we inch closer to these breakthroughs, the philosophical implications also grow. Understanding time more fully could reshape our perceptions of everything from causality to free will. It might even redefine our place in the universe. With each scientific stride, we weave new threads into the fabric of time, each one pulling us toward a future where the once clear boundaries between past, present, and future become blurred. As we continue to push the boundaries of physics, the nature of time will likely become even more intriguing. Time, as we've seen, is not just ticks on a clock, but a rich, complex tapestry that science is still unraveling. This journey through the enigmatic nature of time has taken us from the everyday experience, where seconds can crawl or sprint, to the far reaches of the cosmos, where time itself stretches and contracts. We've explored how relativity paints time not as a universal constant, but as something deeply personal, influenced by speed and gravity. Imagine being near a black hole, where time moves slower, or traveling at near light speeds, where time speeds up for you relative to others. It's not science fiction, it's the reality of our universe. Quantum mechanics has added yet another layer, suggesting that at the smallest scales, time might behave in ways we are just beginning to understand. And with the arrow of time, we see it as a one-way street, always moving forward, never back. Keep questioning and exploring, because every second counts in our journey through the cosmos.